Hello, algebra students. This is a lecture on graphing quadratic functions in either vertex form or in intercept form. We're going to be studying both forms. The previous lecture was on 4.1, which was graphing from standard form. Now we are simply graphing from two additional forms. What are the two forms? Vertex form should look very familiar to us. These three letters, A, H, and K, as promised, are going to be something that keep repeating themselves, and they are thought of as transformations. Just like we did with absolute value functions, the K is going to be your vertical shift, and it will shift up and down the way that you think it would. H is going to be your horizontal shift, and it'll happen the opposite way that you think it would. And A is going to be the stretch or the shrink factor, which is to indicate how steep the function is. And then if there's a negative sign, it's going to be upside down, and if A is positive, it'll be a normal U-shaped graph. So vertex form is the form that's going to look like what absolute value functions look like. We are also going to have intercept form. Intercept form is going to have two sets of parentheses. Rather, this one, has one set of parentheses with an exponent on it. Intercept form is going to have two sets of parentheses. And P and Q are going to be the x-intercepts. Okay, we'll go over what this looks like here in a minute. A is still going to be the stretch or the shrink factor, and if A is positive, it'll open up, and if A is negative, it'll open down. And then this is actually the first time all year that we've talked about the term FOIL, but I know that you guys know what it means. FOIL means first, outside, inside, last, and it's a technique that we use to multiply something like this statement right here, x plus 4 times x plus 7. So essentially what you're doing is you multiply the first two things together. First one in this parentheses, first one in this parentheses, x times x is x squared. And then you do the outside ones. X here is on the outside, and 7, and this one is on the outside, so you'd multiply those and get 7x. The inside two, then you would multiply 4 times x to get 4x. And then we'd also do the last two, the last one in this parentheses would be 4, and the last one in this parentheses would be 7, and 4 times 7 is 28. Oftentimes the middle two will be able to be combined. 7x and 4x make 11x, and this is the expression. These two expressions are the same. They are just in different forms. So this is the vocab that we need to understand section 4.2. Let's go ahead and look at some problems that we might have. This is a function, a quadratic function in vertex form. Okay, remember, vertex form is going to have one set of parentheses with a squared around it. The way that I want you guys to think of this, if you recall, is in terms of transformations. Think back to absolute value functions. -5 at the end would shift down 5, and a -2 inside the absolute value sign, or in this case the parentheses, is your horizontal shift. And horizontal shifts always happen the opposite way that you think they would. So this -2 I would think would shift to the left 2, but it's actually going to go to the right 2. So in order to find the vertex, we would start at 0, 0, just like we did with absolute value functions, but it's not going to be at 0, 0. It's going to be down 5 and to the right 2, our new vertex. Okay. I am, every time we graph, going to expect you guys to list the vertex. So the vertex is at the point 2, -5. And then if we think back to our lecture on section 4.1, graphing from standard form, we know that the axis of symmetry has to go through the vertex, right? Because we're going to have some U-shaped graph, and it's going to look, something like this. I don't know exactly. But this line that goes through the vertex, that's where the axis of symmetry is going to be every time. You can just, if you know where the vertex is, draw a vertical line through it. That's your axis of symmetry. So I'm going to erase this part here because we don't know where that is yet. But that axis of symmetry is going to stay. It's going to go right through wherever your vertex was. And so I can go ahead and list the axis of symmetry. The axis of symmetry is going to be the line x equals 2. And then to get our additional points, remember what I told you guys. Make the little t-table, put the vertex in the middle, do -5, and then count up from there and count down from there. And then we're just going to plug an x value in, and then we can reflect it to the other side of where that vertex is. So instead of plugging in 1 and 3, we can just plug in 1, for example, or 3, for example, and then reflect it to the other side. I'll plug in 3 because it's a little easier. 3 minus 2 is 1. And then we'd have to square the number 1, which stays 1. And 1 minus 5 would be negative 4. We'd also get the same thing if we plugged in 1. Now I'm going to plug 4 in for x. 4 minus 2 is 2. 2 squared is just going to be 4. And 4 minus 5 is negative 1. And we can plug that in as well. So I can go ahead and plot all these points. 2, negative 5 I already have, but I'm going to plug in additional, I'm going to plot the point 3, negative 4, and 1, negative 4, and 0, negative 1, and 4, negative 1. I'm going to connect these points. And there is my quadratic. I also told you guys that whenever you graph, I expect you to list the domain and range. Domain and the range. Remember, the domain is asking what x values does this graph ever achieve. So obviously this graph achieves x values at 2, 3, 4, 5, 6, and actually will keep going forever, right? It'll go forever this direction. This graph is just proceeding. It's going forever up, yes, but it's also moving over. For every time it moves up, it's moving a little bit over, and it's doing that forever. And the same thing this direction. It moves to the left forever as well. I know it's mostly going up, right? As you go left, it's mostly going up, but it's also moving over to the left. So the domain here and the domain for graphing all quadratics, all of this chapter, is the domain is going to be all real numbers. The range, however, is always going to have a restriction on it. This graph doesn't go down forever, right? You guys would hopefully agree with that. What this graph is doing as you go from left to right, it's going down, 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 and then it hits at the vertex, and then it bounces up. So what y values does it ever achieve? Well, it's essentially, if I were to, this is another little trick that I sometimes do to visualize it. That's a horrible, horrible horizontal line. There we go. No y value, if I were to extend this line forever, no y value is ever achieved here. It starts being achieved at negative 5, right? That's the lowest y ever gets to. And then everything above that, every y value above that would be achieved somewhere, right? So this goes up forever. So all of these y values are achieved. Okay, at negative 5, the y is also achieved, but it will never get to negative 6. So we would say all y values are achieved greater than or equal to negative 5. Let's look at another example of this. This plus 5, so here's a new quadratic, right? This plus 5 at the end is going to shift up 5. And this plus 2 on the inside of the parentheses, remember, inside is your horizontal shift, and horizontal shifts always happen the opposite way that you think they would. So I would think plus 2 would shift to the right 2, but it's actually going to shift to the left 2. Up 5, left 2, there's your vertex. So when you're asked to list the vertex, I can do that pretty easily. It's found at negative 2, comma 5. Then also remember the axis of symmetry has to go through that vertex. So the axis of symmetry is going to be the line x equals negative 2. And then we need some additional points, right? All we know right now is where the vertex exists at, but we don't know any additional points. So what we're going to do is we're going to make a t-table. Go ahead and put the vertex in the middle, negative 2, comma 5. What's a little bit greater than negative 2? 1 unit greater than negative 2 would be negative 1, and then 0. And then smaller would be negative 3 and negative 4. Remember, I'm going to be able to reflect this over this line. So plugging in negative 1. Negative 1 plus 2 is just 1. And 1 squared is 1. And 1 times negative 0.25 is just negative 0.25 plus 5. That's going to be 4.75. I do want to emphasize something here, and that is that this whole thing could be typed into your calculator, just as it is, but plugging negative 1 in for x. and it would come up with the right answer. It'll come up with 4.75. So feel free to do that. Then the other thing I want to say is this reflecting trick only works if these are the same distance away from each other. So this is 1 unit away, and this is 1 unit away. So then it's going to work to reflect it. All right, now I'm going to plug in 0 for x. Plugging in 0, 0 plus 2 is 2, and 2 squared is 4. Remember to do the exponent before you do that multiplication. Exponents come first in PEMDAS. So I have 4 right now. I multiply 4 times negative 0.25, and that's just negative 1. And negative 1 plus 5 is 4. So then I can reflect that. I'm going to go ahead and plot these points. I don't think I'm going to be very happy with the points that I've chosen because of the type of function that this is, but we'll take a look at it. Negative 2, 5. Negative 1, 4.75. That's just really close to the vertex still, right? And then 0, 4 is here, and negative 4, 4 would also be here. I just don't have that much information about this parabola at this point, right? All the points are so close to one another. So I'm just going to plug in 1 as well. I know it's kind of a pain, but I feel like my graph will just be better if I plug in 1 as well. So 1 plus 2 is 3, and 3 squared is 9. And then 9 times negative a quarter would be negative 2.25. And then I can add 5 to that, and I would get 2.75. So I just think my graph will be more accurate if I have some additional points. 1, 2.75. And then I can reflect that to the other side at negative 5, 2.75. So I do just feel slightly better about that, and that's what I'm going to go ahead and use. So now as you can see, this graph is just a lot wider. So there's my parabola. Mr. Nyquist has crazy expectations of you to list the domain and the range as well whenever you're graphing from here on out. The domain of this function, if you recall, is all real numbers. This graph goes to the left forever and to the right forever. As for the range is which y values does this graph ever achieve? And in this one, it happens to go down forever, right? These lines are going down forever. So it does start at negative infinity down here at the y's, but it doesn't go up forever, right? It actually never achieves any y value above this imaginary line at 5. So the range is going to be y values less than or equal to 5, right? Which y values does this graph ever achieve? Well, the ones less than 5 or equal to 5, right? So this was some examples of graphing in vertex form. I want to show you some examples of graphing in intercept form next. Intercept form is going to have the 2 sets of parentheses around it. And you are going to graph this in a completely different way. How you're actually going to start this is to think about which value for x would make this set of parentheses 0. Okay? What would you plug in for x to make this individual set of parentheses 0? Hopefully you're coming up with the number negative 3. And then you're going to do the same here. What value for x would make this set of parentheses 0? That is the number 1. And these are actually your x-intercepts, negative 3 and 1. Okay, how did we get those? We asked what makes this set of parentheses 0 and what makes this set of parentheses 0. So we can go ahead and plot those. Negative 3 and 1. Those are my x-intercepts. Up next, I want to find the axis of symmetry. And the axis of symmetry is the middle of these 2 points. Okay, I can identify that in this particular graph. I know that the middle of negative 3 and 1 is just here at negative 1. Okay. However, that's not always going to be that easy to identify. And so what I can do is I can take the average of these 2 numbers, and that'll tell me the same thing. Okay. If I add negative 3 and 1 together and then divide them by 2, that's taking the average of them, right? Adding 2 things and dividing by 2 That's taking the average of the two numbers. So I can do negative 3 plus 1 divided by 2. Negative 3 plus 1 is negative 2, and negative 2 divided by 2 is negative 1. So my axis of symmetry is at x equals negative 1. We know something. We know that the vertex has to exist on the axis of symmetry. This is something that we talked a lot about in 4.1. Okay, the vertex is going to be somewhere along this line. It's got this as its x value. We don't know the y value yet, but we know the x value has to be negative 1. How we can find that y value is by taking negative 1 and plugging that in for x. Okay, take negative 1, plug it in for x there and there. So when you do that, you'd have 2, negative 1 plus 3, and negative 1 minus 1. 2 times, that would be 2, and this would be negative 2. 2 times 2 is 4, times negative 2 is negative 8. So our vertex exists at negative 1, negative 8. That would be right about there. Okay, so we need some extra points. We actually know quite a bit about this graph. We know it goes through this point and this point. But I would like to know what's going on at maybe 0, right? We know what's going on at negative 1 and at 1, but what happens at 0? You could just plug in 0 and see what you get out to figure out what that is, and then reflect it across the axis of symmetry. So if you plug in 0 here for x and x, you'd have 2 times 3 times negative 1. 2 times 3 is 6, times negative 1 is negative 6. So we'd have this point 0, negative 6, and also negative 2, negative 6, because we can reflect that across the axis of symmetry. This would be the graph that we're looking at. We should be able to list the domain and the range pretty easily as well. The domain, of course, is all real numbers because this graph goes to the left forever and to the right forever. As for the range, what y values does this graph ever achieve? This would achieve any y value that is greater than or equal to negative 8. Okay, it starts at negative 8, it never gets below negative 8, but achieves everything above negative 8. Let's look at one more example of this. This would be a great time to pause this video, try it, and then correct it with me, see how you do. So the first thing that you do is you look at the parentheses and you say what makes them each 0, and that would be 2 and 7. So we have this point 2 and 7. Those are the dots for 2 and 7. At this point, you would take the average of these two things, and that's where the axis of symmetry is going to be. The average of 2 and 7, you would add them up and get 9, and then divide by 2. 9 over 2 is 4.5. So there's my axis of symmetry. X equals 4.5. From there, you are going to know that the vertex exists somewhere along this line. So it's going to be 4.5 comma something. And we don't know what that something is, but we can find out pretty easily by just taking 4.5 and putting it in there for x and there for x, which would give us negative 4.5 minus 2 times 4.5 minus 7. This can be a calculator question. You can type that whole thing in. Your calculator will give you the right answer. Or you could do, this individually, this individually. It would be negative. This is 2.5, and this is negative 2.5. We can multiply those things. 2.5 times 2.5 is going to be, these two multiplied would be negative 6.25, and then there's a negative out in front of that, so it would be actually positive 6.25. So the vertex is going to exist at 4.5, comma 6.25. I know a lot about this because I know it's going to go through these 2 points and the vertex, but I'm going to find another point just to be certain or safe and make it look good. I'll plug in 3 and see what would happen. negative, so it's going to be 3 comma, I don't know yet, right? So let's plug in 3, see what we get out. 3 minus 2, and then gross. 3 minus 7. Negative 1 times negative 4, and all of this multiplied together, negative 1 times negative 4 would be positive 4. So 3 comma positive 4. I could reflect that to right there, and I have a pretty good idea of what this parabola is looking like. So we have my axis of symmetry here. We'll do a different color. Axis of symmetry there, vertex there, my domain here. We know what it is. It's all real numbers. Okay, that's about as simple as a test question I'm going to ask you because you can have it memorized, right? As for the range, this graph goes down forever, but it doesn't go up forever, right? It never goes above this y value. Well, what is that y value? What's the highest this graph ever reaches? Well, we know what the vertex is. We know what this point is. It's 4.5 comma 6.25. So this is going to achieve all y values less than or equal to 6.25. I do have 2 more types of questions that you are going to get on your quizzes and tests from this section. One of them is going to be to write equations, quadratic equations from this form, which is intercept form, and I'm going to ask you to convert it into standard form. Okay. Remember, standard form is ax squared plus bx plus c. In order to do that in this question, you are going to take your 2 parentheses and you're going to FOIL them. Okay, that's why we talked about FOIL at the beginning of the lecture. So this 2 will just stay out in front, and I'm going to multiply these things. X times x is x squared. X times 3 is a positive 3x. Then you would do inside 4 times x, that's positive 4x. And then last times last, that's plus 12. Go ahead and combine your like terms. This is going to be y is equal to 2 x squared plus 7x plus 12. And your last step, you're almost done here. You're just going to distribute the 2 to everything. So it'd be y equals 2x squared plus 14x plus 24. This is now in standard form, and you converted. These are the exact same functions, right? I'm going to make another lecture that's talking about how to make sure that you have the right answer here. It's a very simple step, but that's going to be in a separate video. And then we are also going to have this question where this is in vertex form, and we want to convert it into standard form. Now, with vertex form, it is a little bit, there's like one additional step, that's all. This exponent here, what students really like to do that is completely 100% incorrect is to take this exponent, I'm even scared to write this. They take this exponent and apply it to both things inside the parentheses. Okay, that is 100% the wrong way to deal with an exponent outside of parentheses. Instead, what you have to think about is what does it mean to square something? Okay, and what it means to square something, hopefully you're saying to yourself it means to multiply by itself. So what 12 times x minus 1 squared looks like would be actually 12 times x minus 1 times x minus 1 plus 4, right? Because this is taking x minus 1 and multiplying it by itself. Now you FOIL these 2 parentheses. Y equals 12. X minus 1 times x minus 1. First times first would be x squared. Outside times outside would be minus 1x. Inside times inside would also be minus 1x. And negative 1 times negative 1 would be plus 1. And then we have this plus 4 still. Now we would combine our 2 like terms again. Y equals 12 times x squared minus 2x plus 1 plus 4. We're almost done. We are going to distribute the 12 inside the parentheses. Y equals 12x squared minus 24x plus 12 plus 4. In our final step, y equals 12x squared minus 24x plus 16. So this is a lecture on section 4.2. Please do not be afraid to ask me any questions when you are confused.